You will now be placed into conference.
And remember, if you are not asking a question, to please mute your own bridge, as the bridge is open to everybody now.
And in case your phone doesn't have the mute button, *6 mute, *7 unmute. *6 mute, *7 unmute. Any questions? So new or follow-up questions. We welcome all types of questions.
Slide number 12.
Okay.
There is, it says on the bottom, resource block.
Listen, can I help you?
Please mute your bridge.
Okay, the call came into the operator.
If you are not asking a question, please mute your phone. *6 mute. Okay, so you are talking about slide number 12.
Right. Resource block consists of 12 subcarriers.
Okay.
And but just right above that, it says one subcarrier is one symbol. Then why the resource block has 12 symbols instead of, I mean, why does it have a seven or six symbols instead of 12 symbols? Because it says 12 it has a 12 subcarriers, which subcarrier is same as one symbol.
Oh, I see. Okay, let me draw a picture. Okay.
Okay.
Okay, thanks for that question. I will draw a picture, and hopefully that will resolve the apparent conflict. Okay, so I have 10 megahertz spectrum, and inside that I would have 50 resource blocks. Okay, and one resource block, always a dozen subcarriers. Okay, so what I will do now, I will draw just a half millisecond slot. And whenever you're using short cyclic prefix, inside that you will have 7 OFTM symbols. Okay. No more, no less. Exactly 7. So let's call this guy symbol number 0. Then symbol number 1, all the way up to symbol number 6, because inside a half millisecond slot we have 7 OFTM symbols, 0 through 6. Now what do we have inside that tiny 71 microsecond interval? Inside that we have 50 resource blocks, and 50 times 12, 600 subcarriers. So let's say F0, F1, F2, up to F11. Then we have F12, F13, up to 23. And finally we will reach subcarrier 599, because we have a total of 600 subcarriers. So here is the subcarrier number on the y-axis. X-axis is our symbol number. Okay. So now let's talk about our resource block. Okay. So this area that I'm highlighting here is one resource block, and inside the resource block I have my resource element, and one resource element is occupying one subcarrier and one symbol type. Subcarrier number 11 in this case, and symbol number 0. Then we have another subcarrier, another symbol time. So that would be my another resource element, right? So if you observe the entire resource block, we have a total of 12 consecutive subcarriers and it will last for the duration of half millisecond slot. So based on this diagram, now you can see that one resource block would contain 12 subcarriers multiplied by 7 symbols, 84 resource elements, because one resource element is only one subcarrier and one symbol type. So is it clear now or not yet?
Yeah, it's more clear.
Very good.
Thank
Thank you
you.
for your question.
Thank you.
Any other question? More details, better explanation, anything at all? Any follow-up question? Going once, going twice. These types of opportunities do not last for long. So go ahead. Any question? No question for 30 seconds? Then we'll move on with the presentation. But any question at this time? Oh yeah, please speak up. We hear you hardly. As if you were speaking from another planet. Very faint voice. Hello, you had a question?
That may have been background noise, Nisha.
Oh, okay.
I'm not sure.
Okay. No problem. So, okay. So, looks like you like to use this questions box more than the audio bit. So, please maximize the use of the questions box in that case. And no limit on the number of questions. Keep your questions coming. So then, shall we mute the bridge, please?
The conference has been muted.
Okay. So, back to the presentation. So we have basically discussed the timing structure, the types of channels, logical, transfer, physical that we have. And now we are ready to take a look at the types of channels and the signals we have in the downlink. Once we are done with the downlink, then we will discuss what exists in the uplink. So first, downlink. Okay. Let's say we want to deploy our LTE in some coverage area. So this is the area that we want to cover, let's say. Then we have, based on our network planning, we know that, okay, we can have certain cell radius, maybe 3 kilometers, something like that. And then we have this kind of all configuration, 120 degree sectorization, cell alpha, cell beta, cell gamma, right? So basically we are using 120 degree sectorization. And in fact, that is most commonly deployed configuration today. Right. So our cellular networks typically use 120 degree sectorization. So now we have these 3 cells that are controlled by our E node B. So one E node B, our base station, controls 320 degree cells. We have to give every cell a unique identity, so-called physical layer cell ID. Okay, physical layer cell ID. So we have to somehow do the network planning such that we allocate one value out of 504. So the cell ID goes from 0, 1 all the way up to 503. So we allocate cell IDs to every single cell, every single sector. The way we allocate that is we first create groups. Okay. So in this example, we have created this group. So this is a cell ID group. Inside that group, you will observe that there are always 3 cells. Always 3 cells or sector in every group. So we have group number 0 here. And that group has 3 cells. 1, 2, 3. Then we have another group here, group number 1. Right? So that has another set of 3 cells, right? 1, 2, 3, and so on. So basically, we have created a total of 168 groups, and every group has 3 cells, total of 504 cell IDs. So that is the idea. So one cell effectively is given the ID that depends on the group number and the cell number. So let's say we have some UE that is somewhere here, let's say, talking to this cell. So during the synchronization process, we will identify the cell ID. And the importance of that is many other channels are scrambled using the cell ID. So it is very, very important for the UE to know the cell ID. Now this specific UE is inside a cell that belongs to group 167. So this is group 167. That is our group number. Okay. And within that group, it belongs to cell number 2. It is inside the geographical area covered by cell number 2. So group number 167 and cell number 2. So now we know this formula: 3 times the group number and add the cell number. That will give the cell ID. So in our example, we will say, okay, 3 times the group number is 167, and within that group, we are in a cell that is number 2 within that group. So we will get 503. So in summary, a UE will need to identify the cell. 504 cell IDs. And the way to get that is find the group number and find the cell number within that group. So once you know the group number and cell number within the group, you are able to find out exactly in which cell you currently are. Okay. This is how we identify the cell, physical layer cell ID. So think of this cell ID like your PN offset. So in 1X and 1X video, we have 512 PN offsets. So that PN offset will identify a sector. Same way here. A cell ID, physical layer cell ID, will identify a specific cell, a specific sector. And once we run out, then we will just reuse those. Okay. In basic UMTS, we have 512 primary scrambling codes. So once we run out of those primary scrambling codes, then we will again reuse those. Same idea here. Okay. So now we know how to identify a cell. So we need to somehow detect the group number, and we need to detect the cell number within that group. Now, who will help us identify the cell number, identify the group number? The synchronization signal. So the first signal after power on, the UE looks at is this. First signal the terminal will look at. after power on. Primary synchronization signal. There are only 3 sequences. Okay. So basically, one sequence number 0 will correspond to cell number 0, 1 and 2. So now you know that the UE first figures out the cell number within the group by observing the primary synchronization signal. Now there are so-called ZF2 sequences defined in the standard, and they will basically correspond to those 3 sequences. So the UE is programmed with those sequences. It knows how to generate those, and it is just trying to match whatever it receives in the downlink with those 3 options. And one of the 3 options will match, and then the UE knows that, oh, I am in a cell that is sending out sequence number 2, meaning I am in the cell number 2 within some group. We do not know the group number, but we know the cell number within that group. So as the UE, you know the sequence that you are trying to match. But the question is, where is this signal? Right? At what time will you find it? On which subcarrier will you find it? So let's take a look at that. And also, if you recall, we mentioned the slots will help us during the synchronization. So now you will see why we say that. So we have this time slot 0, time slot 10. So within a subframe, of course, we have 10 subframes, and within the 10 subframe, we have 20 slots, 0 through 19. So within the slot number 0 and within the slot number 10, we will send out primary synchronous signal. Remember, we do not send those in any other time slot. No other time slots carry the signal. Only time slot 0 and time slot 10 would carry primary signal. Not all symbols within the symbol 0 will carry that. Only the last OFDM symbol will carry the primary synchronization signal. Only the last. No other symbol is carrying the primary signal. So let's summarize. As far as the time is concerned, the primary synchronization signal is sent during the last OFDM symbol of time slot 0, the last OFDM symbol of time slot 10. So let's pretend that we are a UE. We woke up at this time. So we will not find any match with any sequence. Then we go to the next symbol. No match here, no match here, no match. Aha! Then at this point we find a perfect match with one of the 3 sequences. Then again we will say no match here, no match in any of the other time slots. Now we reach time slot 10. No match here, no match, no. And now when we go to the last OFDM symbol, again we will find a perfect match with our one of the 3 sequences. So in summary, the UE will find the primary signal during the last OFDM symbol of time slot number 0 and 10. Okay. Now this is from the time perspective. The question is, on which subcarrier we will find our sequence? Time we know already, last OFDM symbol of time slot 0 and 10. But how about the frequency? Well, as far as the frequency is concerned, the center 72 subcarriers will carry the primary signal. Okay. So even though we may have deployed the system in 10 MHz bandwidth, for primary signal, we will not use the entire spectrum. We will only use the center portion of the system bandwidth during specific time periods, which is the last OFDM symbol of time slot 0 and 10. That's where you will detect the primary signal from the frequency perspective. So in terms of frequency, the subcarriers are center 72 subcarriers. Okay. And in terms of the time, very little overhead is being wasted. As you can observe from here, very little overhead. We do not consume too many symbols, okay, to send the primary signal. So in LTE, we want to minimize overhead. Okay. So try to minimize as much as possible. So that's the primary signal. So let's summarize. Once the UE has looked at the primary signal, it knows the cell number, whether it is cell 0 or 1 or 2. 1 out of 3 identities it will know. Then it moves on to detect the secondary signal. In the secondary signal, again, it will be helping us with synchronization, and this will help us with group number. We have 168 groups of cell IDs, okay, 0 through 167. And corresponding to every group, we will have a sequence. So secondary synchronization signal is sending out a sequence. The UE is trying to match with 168 options. So let's say that we found a match with group number, let's say 1. And from the primary signal, so this is secondary, we found match with cell number 2. So then my physical layer cell ID would be 3 times the group number 1 plus cell number. So I am in a cell that is number 5. Okay. So now the physical layer cell ID is known to the UE. Now how do we generate the sequences? 168. So we have basically random number generator, and those 2 random number generators will create a PN sequence, random sequence, so-called N sequence. And that's how we figure out the secondary sequence, which is associated with the cell group number. And just like we find the center 72 subcarriers for primary signal, same way those subcarriers will also carry the secondary signal. So from the frequency perspective, both the primary and the secondary signals are using the same 72 subcarriers. However, in terms of time, the last OFDM symbol here of time slot 0 and time slot 10, it carries the primary signal, and the second last carries your secondary signal. So second last here and here. So even though in terms of frequency, same 72 subcarriers in the center part of the spectrum carry your primary signal, carry your secondary signal. From the timing perspective, the last OFDM symbol, primary, second last will carry the secondary signal. So now you know exactly where the terminal will find primary and the secondary signal. Okay, and the question is, will this primary signal contain just 0, 1 or 2? Oh, okay. So actually this primary signal, let me go back a little bit here. Okay, this primary signal is basically a sequence of numbers, and so-called Z of 2. And this is a complex number. So rather than being just 0 or 1, it would be, let's say, A plus J times B, C plus J times D, E plus J times F, and so on. It is a series of complex numbers, not just ones or zeros. Okay, so hopefully that will answer your question. And then, is the primary second synchronous signal in every symbol, or multiple symbols are needed? Multiple symbols. Oh, okay, okay. So if you look at here, let's only here. So from the time perspective, for primary synchronization signal, time perspective, one symbol is good enough. However, during that symbol, the actual sequence goes over many subcarriers, right? So we mentioned 72 subcarriers. So one symbol is okay from the timing perspective, but we will have many subcarriers sending the overall sequence. Okay? So let's say on F1 I send alpha. Okay, okay. Maybe let me do another picture. That will make it a little better. Okay, so from the primary synchronization signal perspective, so time slot number 0 and OFDM symbol number 6. This would be the last OFDM symbol. So now we have, if this is your spectrum, subcarrier, let's say F1 to, let's say 600 for 10 megahertz deployment. So we will use only 72 subcarriers. 1, 2, up to 72 subcarriers. And only one symbol time. So let's say 71 microsecond total OFDM symbol time. So from the timing perspective, we are sending primary sequence only during one symbol time. So subcarrier here will carry, let's say, one complex number, A plus JB. Subcarrier number 2 will carry another complex number. And yeah, actually, if you want to be even more accurate, then we do not use 5 subcarriers on one side of the spectrum. 5 here, not used. So 72 minus 10, only 62 used. So now we have 62 subcarriers carrying 62 complex numbers. And those complex numbers together constitute primary synchronization sequence. So A plus JB, let's say, B plus JD and whatnot. Okay, so hopefully this should fully give you the answer that you were looking for. Okay, good. But of course, anytime you want additional clarity or more information, just type in your question. And again, thank you for a question. Keep typing away your questions. No limit. No limit at all. Okay. So basically, we know how to use the primary signal and the secondary signal. After looking at both primary and secondary, we know exactly which cell we are listening to as the UE. Okay. Cell ID. 1 out of 504 identities. Okay. Then there is a so-called pilot or reference signal. Actually, we do not call it pilot. Okay, the word pilot is not used in LTE. We just call it a reference signal. And those reference signals are specific to cells. Okay. I will just give you one example. Okay. So let's say I have one antenna, and the base station is sending out the reference signal from some antenna. Now, we do not send reference signal all the time or on all the subcarriers because we want to minimize overhead. So we said, okay, let's say I have one resource block, 12 subcarriers, and this is my slot, half millisecond slot, and of course we will have 7 symbols inside that slot. Okay. So I will send my reference signal during symbol number 0 and symbol number 4. So 6, 5, and 4. 0, 1, 2, and 3. Okay. Tiny handwriting. We don't have much real estate to work with. Okay. So we have 7 symbols. Out of 7, symbol number 0 and symbol number 4. During those 2 symbols, we will find a reference signal. Okay, let's pick symbol number 0 here. During symbol number 0, who will carry the reference signal? This subcarrier number F0 and subcarrier number 6. So in one specific cell, subcarrier number F0 and subcarrier number F6 is carrying our reference signal. So that's what happens during symbol number 0. Everything else here that you see, the normal empty rectangles, all those empty squares, rectangles, they carry the data. User traffic. Okay. Similarly, during symbol number 4, some other subcarrier will carry the reference signal here and here. So if you are interested in the numbers, this would be number 3, this would be subcarrier number 9. So as you can see, we are trying to minimize overhead, and as a UE, the UE will know exactly during which symbols and on which subcarriers we will find our references. Similarly, if we have multi-antenna transmission, 2 antenna ports, then this picture will tell you which subcarrier and symbol will carry the reference signal from both the antennas. We support up to 4 antennas. So the standard defines the symbols and the subcarriers for all the 4 antennas. Okay. So we discussed primary signal, secondary signal, and reference signal. Now, let's look at the broadcast channel. Okay. Because since we already know the primary synchronization signal, secondary, we know the cell ID, so we will be able to descramble the broadcast channel. This broadcast channel is scrambled by the cell ID, but we already know the cell ID, so no need to worry about that. Again, it is sent on specific time frequency resources, okay, and it carries master information block. So the physical broadcast channel always carries a master information block. And exactly which resources carry the broadcast channel, I will give you an example in next few minutes. But assume that as a UE we know where to find the broadcast channel. And on that broadcast channel there is master information block. And if you are interested, then the logical channel is broadcast control channel, transport channel, broadcast channel, physical channel is physical broadcast channel. So we have the mapping. defined in the standard. Now, what is inside the master information block? Very important. It tells us, for example, how much is the bandwidth? Okay, now if you have observed, if you look at primary signal, secondary signal, even the broadcast channel, all of those, they are in the center part of the spectrum, center 72 subcarriers. So if you want to detect primary signal, secondary signal, or the broadcast channel, you do not even need to know how much bandwidth we are using, because you will always detect the signals in the center portion of the spectrum. So regardless of how much spectrum we are using, whether it is 20 megahertz deployment, or whether it is 10 megahertz deployment, or 5, regardless of that, primary, secondary signals and the broadcast will always occupy the center 72 subcarriers. So we do not even need to know the bandwidth when we are looking for these three signals in the channel. Okay. However, once we look at the broadcast channel, which is of course carried by center 72 subcarriers, one piece of information is the system bandwidth. So only after observing and decoding the broadcast channel, the user will know that, this is a 10 megahertz deployment. Okay. Until that point, we have no idea about the bandwidth used inside that system. The frame number, so every 10 millisecond radio frame has a number, and we can find the number of the frame from the master information block also. There is a so-called PH, physical hybrid ARQ indication channel. We will take a look at that later, but basically that's a channel to support uplink hybrid ARQ. Don't worry about that right now. Right now, this is the important that after observing the master information block carried by the broadcast channel, DUE figures out the system bandwidth. So at what time will you find the broadcast channel? On which subcarriers will you find broadcast channel? Those are the answers you will get now. So let's pick the, let's say, frame, 10 millisecond frame, radio frame, and 4 consecutive frames will carry the master information block. So same information in 4 consecutive frames. 4 consecutive frames, 10 millisecond frames will carry MIM. So 10 millisecond multiplied by 4, 40 milliseconds. So this is that 40 millisecond window. So within the 40 millisecond window, same information is inside every single frame. So let's pick this frame. Inside that frame, we'll have 10 subframes, 0 through 9, total of 10. And we will not see the broadcast channel in all the subframes. We will see the broadcast channel only within the first subframe number 0. And even within the subframe 0, where will you find the broadcast channel? Symbol 0, 1, 2, 3 in the second slot. Okay. That's it. So in summary, we know now exactly at what time we will find the broadcast channel. In terms of frequency, center 72 subcarriers. Question. I will give you maybe 2 or 3 minutes, and please participate in the poll. True or false? 50% chance of being right. Let's see if we can improve upon our record. The first question, 66% accuracy. Second one, 72. Now let's see whether we are doing better or we are doing worse. I need your help. So if you are not sure, do not give any answer. Just kidding. You have to pick. You have to participate. And if you do need to look at the PDF file, no problem. Go ahead. But give me something better than 72%. Now, if you want to answer this question correctly, then you need to know the following. Where are those signals and the channels? The primary, secondary signals and broadcast. Where are those? So if you know in terms of frequency, if you know where they are, then you will be able to correctly answer the question. In terms of frequency, which subcarriers carry those signals? That will tell you the answer to this question. Okay, I will give you, let's say, 2 minutes. Let me give you more time. So far, I have got 13 answers. The return rate is quite poor, 26 students. So please participate. I will give you 1 more minute. Think, where are those signals in terms of frequency? Do we have specific part of the spectrum? Or you will find them all over the place? If you find them all over the spectrum, then we will have to know the bandwidth. If they are sent in specific portion of the spectrum, then we do not need to know the whole bandwidth. So think where they are. Where are those signals? Where are they hiding? Okay, let's see what we got. Okay, little better than last time. So we are improving. 77% accuracy this time. Very good. So yes, no need. Okay, we do not need to know the whole bandwidth because they are always in the center part of the spectrum. Center 72 subcarriers. It doesn't matter whether we are using 5 megahertz deployment, whether it's 10 or 20. It does not matter. So that is the answer. And thank you for participating in the poll. Let's move forward. Oh, we have one more question. So we have about 77%. Okay, so let's see if we can do even better than that. I, of course, like 100%, but give me something close to 100%, if not 100. If you need more time, I will give you more time. Okay, we need to look at, what do we need to look at? And then we will know the cell ID. Okay, so basically we need the group number and we need the cell number within the group. Group number and cell number. So what will help us find that? Maybe 3 minutes. I will give you 3 minutes. And once we are done with everything If we have some time, then I will summarize all the channels for you. So let's see how much progress we make. Again, this is open book, open mind, open everything exam. Hopefully you should not read any of those. Just keep your mind open. That should be good enough. You should not need the books. But if you do need to refer, no problem. Go ahead. You can use the PDF file without any problems. Okay. Let's show the results. You made me happy. So 82%. Okay, so we are gradually making improvements. Okay, so that's the correct answer. Primary signal will give us the cell number within the group. Secondary signal will give us the group number. So the cell number and the group number together will give us the physical layer cell ID. So it is good enough just to observe primary and secondary synchronization signals to be able to calculate the physical layer cell ID. Again, thank you very much. Thanks for your participation. Okay. So let's move forward now. What did we look at? We looked at primary synchronization signals, secondary synchronization signals. So they are helping us with the timing, frequency synchronization, and also identifying the physical layer cell ID. Then we looked at the broadcast channel. Again, broadcast channel, center part of the spectrum like primary and secondary. And that gives us so-called master information block. And master will tell us, okay, we are using 10 megahertz bandwidth in this cell. And we can identify the cell specific reference signal also, because they are sent on specific subcarriers during specific symbols. So we can look at all those signals. Okay. And now we will start moving toward the data channel. Okay. So we mentioned that we can change the data rate in LTE very, very fast. So let me ask you a question. How fast can we change the data rate in LTE? In LTE, how fast can we change data rate? Every how many milliseconds? Okay, let me see. Every millisecond. Perfect, perfect. Thank you for your answers. Very good. So every millisecond we can change things around. And the way to do that is early part of the subframe, let's say 1 millisecond subframe, early part would contain the control channel, so-called physical downlink control channel. Sorry about the acronyms, but we can never escape acronyms, right? But the good news is that you have the PDF file that has all the acronyms. Hopefully we did not forget any acronym. But physical downlink control channel, that's what will give the UE both the downlink allocation and uplink, because this is sent by the E node B to all these UEs, right? So there is this control channel, physical downlink control channel. gives the UA uplink resources, allocates the UA downlink resources. Everything is allocated by the E node B using that channel. Now the standard says that that control channel could occupy 1, 2, or 3 OFDM symbols. Okay, so the standard says that we could consume 1, 2, or 3 OFDM symbols inside every subframe for the control channel, and the control channel will carry the allocation. Okay. Now the question is, within this specific subframe, I have this subframe. As a UE, I need to know how many symbols are occupied by the control channel. So if someone tells me that, oh, inside this subframe we have 2 OFDM symbols that carry the allocation, then as a UE, I will process the first symbol, then I will process the second symbol, and then I will see, do I have any allocation for that subframe? Did E node B give me something for my downlink transmission, for my uplink transmission, for my downlink reception, for uplink transmission? So we need some way of knowing how many symbols occupy the control channel, and the answer to that question is this channel, physical control format indication channel. So basically it tells us how many symbols are occupied by the control channel. So basically it would say one of these numbers, 1 or 2 or 3. So if we find out that, oh, right now only 1, so it means that inside this subframe, I just need to look at the first OFDM symbol, symbol number 0, and look at the control channel inside only that symbol number 0 to see if there is any allocation or not. That is the idea. So in summary, the control format indication channel will tell us how many symbols are occupied by the control channel inside that subframe. So from one subframe to the next subframe, we can have different answers. So maybe right now, the control channel occupies only one subframe, but it is possible that in the next subframe, the control channel will consume maybe 3 symbols. Let me ask you a very simple question. Let's say I have many users, and I want to convey allocation to all of those users. Should I use 1 symbol for the control channel or 3? Okay, so for many users, I want to convey resource allocation. Should I use 1 OFDM symbol or 3 symbols for my control channel? 1 or 3? 3. Very good. Very good. Thank you for answer. Because I want to convey allocation to many users. So I need more resources to convey the information to the user. That UE number 1, I am giving you 1 resource block. UE number 2, I am giving you 10 resource blocks, and so on. So I need more resources of the control channel to convey allocation to many UEs. So basically, I have little bit more overhead because I need to give allocation to many UEs. However, on the other hand, if I just have 1 or 2 users and I want to convey allocation to those, no need to consume more than 1 symbol. 1 symbol is good enough. So the existence of this channel is helping us control the resources that we consume for the downlink control channel. So dynamically this channel will tell us that inside this subframe, how many symbols will be occupied by the control channel, and based on that knowledge, our UE will process those many OFDM symbols to figure out if the E node B has allocated any downlink or uplink resources or not. Where will you find that channel? Well, very easy. Basically, it is sent, distributed in 4 different chunks throughout the spectrum. Okay. So if I have 20 megahertz spectrum, then I have 1200 total subcarriers. I want to send this channel uniformly spaced. So I have 4 chunks divided by 4, 300. So every 300 subcarriers, I will have the resources that will carry the control format indication channel. Okay. And once we look at the control format indication channel, we will know how many symbols are consumed by the downlink control channel. This is a very, very important channel, downlink control channel. So it allocates not only the downlink resources but also the uplink resources. So for example, let's say that I have maybe 2 UEs in my cell. So here is my cell. Okay. 1 UE here, another UE here. So I would say that okay, one control channel, I would say this is for UE number 20, and I am giving the UE, let's say 15 resource blocks for downlink transmission. Then I would say okay, another control channel number 2. This is for UE number 2, and I am giving UE maybe 20 resource blocks for maybe uplink transmission. So as you can see, the control channel will convey the allocation, right, for not only the downlink resources but also the downlink reception. The UE is getting data in the downlink. So we are giving the resources not only for downlink reception by the UE but also uplink transmission by some UE. So both uplink and downlink resources are under full control of the E node B. So in OFDMA system, the E node B is in complete charge of the situation, commander-in-chief. Okay. The US can only make a request, but the actual resources are allocated by the E node B scheduler, both for the downlink and the uplink. And we use the help of this control channel to convey the allocation. And we can change those things every millisecond, every subframe. We can allocate different numbers of resource blocks for uplink and downlink transmissions. Okay. The resources are specified in the so-called unit of downlink control information. There are several formats of so-called DCI, and the allocation is specified for a UE based on the identity of the UE, CRNTI, Cell Radio Network Temporary ID. Cell Radio Network Temporary ID. So think of CRNTI as your Walsh code, as your MAC index in DO, like OESF code in UMTS, because that is the dedicated identity of the UE for the air interface. Okay. Air interface. So when I convey the allocation to the users, let's say I want to convey uplink allocation to user number 2. So I will have this control channel. I will send DCI format 0. Okay. So I am giving 20 resource blocks. So I create some sort of message. 1001, something like that. And this message effectively tells the UE that we are giving 20 resource blocks. Then we calculate CRC. Cyclic redundancy checksum for the message. And then we will scramble CRC using identity of the UE. So now whenever UE1, okay, in this case UE number 2. Let's say we are UE number 2. So we will look at control channel 1. But control channel 1 is for another UE. So there is no CRC match for us. So we said, okay, let's be optimistic and let's go to the next control channel. So we go to the next control channel number 2. This control channel 2 will be using our identity to scramble the CRC. So now we will find perfect CRC match. So we are happy. We know that, oh, we got some allocation. And pretty good allocation. 20 resource blocks. So we are happy and we will be sending a lot of data using those 20 resource blocks. So that is the idea. That's how we allocate resources. Uplink resources and the downlink resources to the user. Okay. So in summary, the physical downlink control channel conveys uplink and downlink resource for the user. Different formats are defined, so this is for your information. I will just summarize that. Okay, for uplink resource allocation, we use one format. If you want to use advanced antenna techniques such as MIMO, multiple input, multiple output, so-called spatial multiplexing, you will use this format. If you want to do power control commands, then you can use some other formats. So basically, different formats exist for different reasons. Okay, and the UE will try various formats for the control channel. So that's what we say is called blind detection. So for example, if we have symbol 0 for the control channel, the UE will say, oh, do I have control channel here? My CRC match? No, no problem. Do I have CRC match here? Do I have CRC match here? So it will keep looking for this allocation by processing all the control channels that may exist. We got a question for RV. What is this RV? It is not recreation vehicle. It is redundancy version. Redundancy version. Basically, redundancy version means that which turbo code symbols are sent over the air. Turbo code symbols. Okay. So let me just give you quick 1 minute view of that. So here are my bits going into the turbo coding block. Then we got, let's say, 1000 bits going in, 1000, 3 sets of 1000 bits, total of 3000 code symbols are coming out. this is called systematic. So called parity 1, parity 2. So let's say redundancy version 0. We said, okay, let's put all the systematic bits. And then I have some space left for, let's say, 500 bits. So I would pick 250 from parity 1. And then I will pick 250 from parity 2. If I have another redundancy version, let's say number 2, then maybe I have space for, how much space did I have? 1500? Yeah, so I would put maybe 750 from parity 1. I will put from parity 2, 750. No systematic bits. So redundancy version basically tells us which turbo code symbols we are picking. Okay. So redundancy version. Okay. So hopefully you get enough details there. But anytime you want more details, more explanation, just type away your question. Yeah, we are supposed to be recording, so hopefully you will have a recorded session that you can refer to in future. Okay. Okay. Another channel that we have, physical hybrid ARQ indication channel. So basically, this is to support uplink hybrid ARQ. So the idea is that whenever the UE sends a packet to the E node B, packet P, the E node B says, yes, I got your packet without any problems whatsoever. Positive acknowledgement. So in that case, no need to retransmit your packet P. We need some channel that sends this kind of acknowledgement, and that's why we have the physical hybrid communication. And in case we have some problem, let's say we say, oh, we could not decode the packet correctly. If there is no problem, I will then retransmit that packet P. That is the basic hybrid ARQ. So we are sending the hybrid ARQ positive or negative acknowledgement on the physical hybrid ARQ indication check. And one channel carries one echo neck. The BPSK modulation, so that it is very, very easy to reliably detect the echo neck. And which specific subcarrier, for example, would carry the echo neck? So that would be sort of a function of actually the resources we allocated to the UE. So if we, let me give simple example. Let's say we give for uplink resource block number, let's say 30. Okay, so that would mean that, for example, the hybrid ARQ indication egg or neg would be on downlink, maybe resource block number 10, something like that. So we will have a fixed mapping defined in the standard. So UE knows which resource block would carry the egg or neg for the hybrid ARQ for that specific UE. Okay, we have a question. The difference between ARQ and hybrid And this hybrid ARQ is not new in 4G LTE. We do that even in 1xc video or HSDP, HSUP. The basic idea is ARQ, stands for automatic repeat request. Thanks for a question. ARQ, and this is a hybrid automatic repeat request. Okay. Simple ARQ means identical information retransmitted. And hybrid ARQ means that different information and specifically different code symbols sent over there. So for example, let's say I have my packet P 100101. Okay. So in simple ARQ, what will happen is after we send this packet P and we have some problem, error P. Okay, so then we will retransmit P. So it is the same information. Okay, and that normally takes let's say 100 to 200 milliseconds. Okay. Some technology even 500 milliseconds. Okay, but now if you contrast that with hybrid ARQ, then let's say we send packet P. So this is 100101. Then we have some negative acknowledgement. Then we send this packet P prime. So maybe 011100. So we have now different sets of bits, different code symbols, turbo code symbols, even though they are representing same original bit, same packet P. But the actual information going over there is different. We are representing the original packet P in a different form. And we are picking different code symbols based on the redundancy version. The beauty of hybrid ARQ, the delay is let's say about 8 milliseconds in LTE. But if you do if you do normal ARQ, then delay will be little longer. Okay. So if you want to tie all those things, physical layer, MAC, RLC, PVCP, RRC. This is only for signaling messages. RLC, which is equivalent to RLP in 1xc video, radio link control. This will do the ARQ, simple read transmission. And the physical layer here does the hybrid ARQ. Okay, so basically when physical layer fails, RLC will do the retransmission. RLC fails, then TCP will do the retransmission. We have 3 levels of potential retransmission in TCP/IP based system. Hopefully you got enough information in response to your question. Okay. Thank you for a question. Okay, what do we have now? Physical downlink share channel. This is your big pipe, as big as 300 megabits per second. Right? That is the highest data rate supported in the downlink of LTE system. Okay. And where do we really get our data? Completely up to the E node B scheduler. So the control channel gives us the resources, and using those resources, we will get our actual data. So basically, if the E node B has conveyed through the control channel that, oh, we got physical resource blocks, maybe 1, 2, 3, and 4, then our UE will then look at that subframe that, okay, here is my time, the x-axis, the y-axis here. So one of the comments we got was, sometimes my handwriting is difficult, so I'm trying to improve that using the constraints of live meeting. So hopefully you can still decode. Okay, and then these are my physical resource blocks. Okay, so we got 1, 2, 3, and 4. Very good. So we have 0, 1, 2, 3, 4, etc., etc. And we got 4, so here. But of course, the early part will be your overhead, control channel, and some other channels. We ignore that. So during the remaining portion of the subframe, those resource blocks, okay, would carry our actual data. So that is our physical downlink shared channel for all practical purposes. Okay. So in summary, the downlink control channel has given us some downlink resources, and using those resources, we will retrieve our packet. So that's for data. Also, we can send a page message, okay, system information, etc. So a lot of things we can do using this big pipe, as big as 300 megabits per second. And the largest transport block size that we can send, think of that like a packet size, is 151,000 approximately. And within 1 millisecond interval, we will be able to send 1 or 2 transport blocks. So if you are sending 2 transport blocks, multiply that by 2, so you will get about 300,000 bits. Divide that by 1 millisecond, and that's how you can get 300 megabits. If you do want to do frequency hopping, it is supported. Different transmission modes. So you can do single antenna transmission, you can do transmit diversity, spatial multiplexing, MIMO, multiple input, multiple output. Do not worry about those things. We will cover that later in another session. We have one whole session dedicated to antenna tech. And we can pick which blocks we want to allocate to a specific user. One or more resource blocks can be allocated. Okay, so that's your big pipe, okay, physical downlink shared. Let me ask you a question. So I will give you maybe 3-4 minutes. So please think carefully and then click. Our last time, I think we got about 80%. Yeah, so let's see if we can do better than that. So that is our minimum goal, minimum performance requirement, 83%. If you are not able to break that, you have to come back and listen to my voice again. So you better give me greater than 83% accuracy now. I'm so tempted to close the poll because right now I have 100% accuracy. But I got only 3 answers so far. So please think carefully and help me achieve my goal of 83% accuracy. I will give you 4 minutes. So you have enough time. So think carefully and then pick your selection. And by the way, thank you for your questions and answers. No need to rush. think carefully and then pick your choice. And we are looking for a statement that is not correct. Not correct. And I will give you some info. See, hybrid ARQ. Basically, so now we are from 83% down to close to 70%. So we need to make up for this, okay, in the next 4. So you better pay attention and give me close to 90% next time around. Okay, so let's discuss this. The first one, the control format indication channel. Yeah, I understand maybe because of the acronyms, it may be a little bit difficult, but what can we do, right? We can never avoid those. But basically, control format indication channel tells us how many symbols are consumed by the control channel. So that is correct. So we cannot choose that as our answer. The second one, control channel allocates both the downlink resources and uplink resources. So here we are saying that, oh, it cannot allocate uplink resources. That is not true. So option number 2 is not a correct statement. So we need to choose that as our answer. The downlink shared channel, couple of you chose that one. So basically it carries your traffic, it can carry system messages, it can carry page messages, anything that you want to send. Okay, that is your big pipe. So you can do any kind of transfer of traffic, signaling messages or whatever using the big 300 megabits per second pipe. Okay. Okay, very good. But we do need to compensate, okay, for the about 10% loss that we had for our accuracy. So next time we need to make up for that. So keep that in mind. Okay. So having done that, let's have a short break, 10 minutes, and then we will take care of